All right, so for our acceleration problems here, okay, in our first one, we got a large rock rolling down a hill towards a road. Okay, when a driver passing by first sees the rock, it is traveling at 7.5 meters per second. So that would be our initial velocity. When the rock reaches the road, it's traveling at 13.5 meters per second. Final velocity. Okay, if the rock was accelerating at 4.4 meters per second squared, that's our acceleration. How long does the driver have to stop? We're looking for time. All right. So give them a mark first for their givens. We were given acceleration, initial velocity, and final velocity. Okay, so 1 mark for those. You can give them another mark for realizing it was an acceleration question, which is really a gimme since the name of the quiz was acceleration quiz. Okay, but we'll give it to you anyway. We got to manipulate for time. Okay, in order to manipulate for time, we multiply both sides by time. Time comes over here. Okay, we divide both sides by A. A ends up over here. So give them a mark if they have that manipulation. All right, give them another mark for plugging in the numbers correctly. Final velocity, 13.5, minus initial velocity, 7.5, divided by acceleration, 4.4. Okay, now if they only did one of the 2 steps, but it's right, you can give them both marks because they knew what to do. Okay. And then that should equal out to 1.36 seconds. If they rounded to 1.4, that's fine. Okay? So that one's out of 5 marks. Any questions on that one? Okay, for the second question, we got Wile E. Coyote, and here's the key on this one. Drops an anvil. Okay? In an attempt to catch the Roadrunner. If you drop something, how fast is it going initially? It's not. So its initial velocity is 0 if you drop something. If you recall, in the podcast on Tuesday, okay, when I was at the track meet, the first question I did on that was the one with Mervyn the Menace dropping the water bomb, and it was the same thing. Dropping means initial velocity is 0, and I spent some time talking about that in that one. Okay, so our initial velocity is 0 meters per second. Our final velocity is unknown. It says it falls for 6.5 seconds, so that's our time, and all things fall at the same rate on Earth of 9.81 meters per second squared. Okay, so A equals VF minus VI over T. You can give them a mark for that, as well as the mark for their givens right here. Okay, manipulate for VF. So first thing we do is multiply both sides by T. So T comes over here, and then we add VI to both sides. So it looks like that. All right, so our final velocity, there's the manipulated formula. It doesn't matter whether they have VI plus AT or whether they have AT plus VI, or if T is before A, it doesn't matter. Okay. All right, give them another mark for plugging in the numbers. 9.81 times 6.5 is really all they need, because adding 0 doesn't really do anything mathematically. All right, and then our final answer, 63.8 meters per second. All right, they must have the meters per second to get that mark. They do not require down or negative, because the question asked how fast is it going, which does not require direction, because that's asking about speed. Okay, if it had said at what velocity is it traveling, you would have had to say 63.8 meters per second down. Okay, something like that. Caleb, question? As long as he's got givens written down, he gets the givens mark. After that, then he'll lose them. She didn't write this, but she plugged in numbers. It's fine. Give her both marks. Yeah. Okay, so the whole thing's out of 10. Give him a mark out of 10. Put it in the box, please. Okay, then hustle back to your desk and take out what we were working on yesterday. Okay, listen up here, guys. Before we get back to work and energy, I have a number of assignments that are not done here for the Need for Speed Lab. Okay, and between all 3 of my classes, I had a number of emails and such. Okay, last night and today, you know, about well, Mr. Coder, this isn't working, or I can't make that happen, or blah blah blah. Okay, When do I always tell you to do your assignments? Ahead of time, not the night before. Okay? Fate knows when you are most vulnerable, and it is always the night before something is due. Fate is cruel and will take advantage of said situation. All right? That is when your computer will die. Okay? Your internet will go down, or Google Classroom will flake out. Okay? Yeah, that's what happens the night before things are due. So please, 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 for like the 5th or 6th time this year, don't leave stuff till the night before. Okay? Tomorrow, remember, is obviously Friday. But remember that the long weekend starts at 12:25 tomorrow. It does not start at 3:32 today. That's my nice way of saying you have to be at school tomorrow. Tomorrow is a school day. The long weekend holiday is Monday. Monday. That's the day off. Okay? Yeah. All right. Okay, so yesterday we talked about this work energy theorem thing, and today we're going to look at the problem solving that goes along with that. All right? Now, the work energy theorem says that work is a what? Is a change in energy. Now, while we can memorize that and we can regurgitate that onto a test easily, the big challenge here is this: being able to apply it properly and read a question and know that that's what the question is asking about. Okay? The biggest challenge, guys, in physics is no longer your math ability. Okay? I mean, we looked at, Mr. Dickey and I looked at the physics diploma exam the last few semesters, and there's a major trend towards reading comprehension as opposed to mathematical ability, which, you know, we're kind of okay with. Physics shouldn't just be about people who can get 100% in math should get 100% in physics. It shouldn't be about that. Okay? It should be about who understands physics the best. But in order to do that, they have to have a lot more stuff to read. Okay? And honestly, when we looked at the last one, we thought the amount of reading comprehension bordered on savage. Okay? Like, there were several questions where we, as physics teachers, read through this big long passage and then went to the questions we were supposed to answer and went, I'm going to have to read that again because I don't remember reading anything about that. And we had to go back again. Okay? So reading a question carefully and writing things down as you go is a really important skill for doing well in physics, believe it or not. Almost important as reading is in English. Okay, in English class, obviously you got to be able to read and interpret stuff. Okay, when you read a play or you read a book, okay, and you want to find the themes and all of that. It's just as important in physics, except we're not looking for the artsy stuff. Then we're just looking for the what did this question tell you, as opposed to how does this one make you feel? Okay, yeah, we're just a little different on that. Okay, but it's still important to be able to read through the question, okay, and find out the important stuff. And the context of a question tells you a lot about that. All right, here's what I mean by context. If a question is talking about, let's say, a vehicle changing its speed, we're talking about a change in what kind of energy? Kinetic, right. It's changing its speed, so we're changing the kinetic energy. We'd probably also be changing chemical because we'd be using fuel. But we're looking at mechanical energy here. So we're looking at a change in kinetic energy in a question like that. That's where, okay, I read the question and I understand that this is going on, and that means there's a change in kinetic energy. Okay? Whereas if I'm reading a question about a person climbing a ladder, that's a change in, they're climbing a ladder, they're going up, so that's what kind of energy? Potential energy, right? That's what I mean by being able to read a question and interpret what's going on. Because knowing now that there's a change in potential energy tells me two things. I'm dealing with potential energy and work is involved because there was a change in energy. So being able to read a question carefully tells me lots about how to go about solving it. Okay? And that's what we're going to look at a lot of today. All right, so yesterday we ended off with the example about how much work it takes to stop your car, okay, when you're traveling at various speeds, and the exponential relationship between speed and stopping distance and speed and energy. That was actually the first example of a work energy theorem problem that you might encounter in Science 10. Okay, we had an initial amount of energy, we had a final amount of energy. Because energy changed, work was done, and we were asked to calculate something about the work, either the distance over which the force was exerted or the force that was being used. Okay, those are the kind of things you're going to be asked to find. Right, so that's the kind of stuff we're going to go over today. All right, so what I want you to do right now is copy down this example, and then we're going to go through it together. So I'll give you a minute to copy it down, and then we're going to go through it. So as we read through this question, we want to do two things. We want to write down our givens, and we want to interpret the context of the question in order to find out what type of energy is changing or what's going on in the question. Caleb, question. 0.125 kilograms, yes. All right, so as we're reading through here, it says a rubber band is stretched 0.85 meters. What does meters measure? It can measure distance. It can also measure height. In this case, it obviously measures distance because it's not a vertical thing. We're stretching this rubber band, all right? So it's a distance. So decimal 85 meters for that one. Okay, by a force of 60 newtons. So what is that number? 60 newtons is a force, right? It says a force of 60 newtons, right? Again, it's just important to read through. In case we don't remember what newtons are units for, okay? Newtons are the units for force, by the way, okay? But in case we don't remember that, the wording of the question basically told us force is 60, okay? All right, so I've been given a distance and a force. What's going on in this question? Those two things can be used to calculate work. Okay, work is being done in this question. If I've got a force and a distance, work's being done here. All right, at what speed? All right, speed. Speed's something we don't know here. Okay, would it propel a 0.15 kilogram ball, mass is in kilograms, when released? Okay. So there's a few things going on in this question. A rubber band is being stretched, so work is being done there. And that's changing the potential energy, elastic potential energy of the rubber band. But the question doesn't really ask me about potential energy or really anything about the rubber band. It tells me some stuff, but doesn't want to know anything about the rubber band. What it wants to know is something about the speed of this ball. All right? So what I have to do is visualize what's going on. If I have a rubber band and I put a ball in it and I pull it back, how fast is the ball going when it's sitting in the rubber band and I'm holding it? 0. All right. Does the ball have any energy at that point? Actually, the ball doesn't have any potential. The rubber band does. Okay? Well, we're assuming it's on a table. Okay? So yeah, there's no possibility that it could fall. All right? So the ball doesn't have any energy of any kind initially, does it? It certainly doesn't have any kinetic because it's not moving at that initial point. All right, so this is part of that interpreting a question. Okay, these things aren't outright said to us, but we have to interpret them. All right, it wants to know its final speed. What kind of energy is involved with speed? Kinetic or potential? Kinetic, right? Kinetic energy has to do with speed. All right? Think about this, guys. Here's our formulas. Potential energy has to do with mass, gravity, and height. And I wasn't given any of those things. And there was no talk of anything vertical. Okay? Kinetic energy is 1/2 times the mass times the speed. So speed and mass have to do with kinetic energy. Height, gravity, and mass have to do with potential. All right? So this question is asking about kinetic energy. That's what's being changed for the ball. When the rubber band is released, the ball will accelerate and its speed will change. So its kinetic energy will change. And a change in energy is work. All right, that's where we start. Work is a change in energy. And specifically in this question, it's a change in what kind? Kinetic. All right, so that's the thought process we want to go through. Is work being done? Yes. Okay, that means energy is changing. What kind of energy is changing? Now I'm off. Okay, now I can get moving on this. All right, do we have a formula for work? Work is force times distance. Okay, work is also a change in energy. That's what we wrote up here. So how do I write change in kinetic energy? Change always means minus. What two things do I minus? Yes, which energies? The initial and the final. So change in energy means EK final minus EK initial. I know my penmanship is bad, but those are English letters. Okay? It's not like Cyrillic or anything like that. Okay. All right. I've got final kinetic energy, and I would assume that in a situation where I shoot a ball with a rubber band, the final velocity is going to be something other than 0. Agreed? Since that's what it's asking me to find. But what's the initial velocity? So what's the initial kinetic energy? Also 0. So I can just take that right out of there, can't I? That's good because that makes my formula a lot easier, right? Don't have to deal with any minuses or any other parts of it. All right, I have a formula for kinetic energy. I'm going to plug that in now. Force times distance equals 1/2 times the mass times the speed squared. Okay, I could put the F here, but it's kind of redundant now that there's only one. All right, but we'll leave it there anyway. I'm trying to find VF. So I need to get it by itself. So now I got to follow the rules of algebra. If I want to move something, I do the opposite. I want to leave VF where it is. I want to move other things. How do I move the 1/2 and the m away? Divide them, right, because they're all being multiplied here. All right, so I divide them over to this side. All right, so force times distance divided by 1/2 the mass equals VF squared. Do I want VF squared or VF? I want VF. The question didn't ask what's the square of the velocity. It said how fast is it going. All right, how do I get rid of the square? Square root it. All right, so I square root that side and the square goes away. Rules of algebra say I square rooted that. I got to square root the left side. Okay? That's probably the trickiest manipulation you'll have. Okay? I mean, and really, have we done anything like extraordinarily complex? All we've done is follow the rules of algebra here. If I want to move something, I did the opposite. And what I did to one side, I did to the other. I haven't even used the second half rule yet. Okay? All right. Now I'm going to plug in my numbers. So the force was 60 newtons times 0.85 meters divided by 1/2 times the mass. That's going to get me VF. Okay. Now, if you're really confident in your ability to use brackets and stuff, you can go ahead and plug this all in one step. Okay? I would say if you're not really confident, and you haven't done a lot of stuff with using brackets and making your calculator do stuff right, I wouldn't do it. Okay? I would just do this piece by piece. So I'm going to do 60 times 0.85. Whoops. Yeah, 60.85 is 60.85. They're right about that. 60 times 0.85. All right, it was 51. Now I'm going to divide that by the bottom. Now I do have to put the bottom in brackets here because I want the whole bottom. Okay? All right, 816. Now what do I have to do? I got to square root that. I've done everything else. Now I square root. All right, so second square root, and I'm just going to get the answer to go in there. Okay? All right, so it's going to leave the rubber band at 28.6 meters per second, which is pretty fast. It's also a pretty small ball. Okay? 125 grams is not very big. Okay, do I need to put a direction on that? Nope. In fact, I have no way to know what it is. Never mentioned it in the question. And it asked for speed, so okay, I don't have to put a vector on it. Yeah, most of the time it won't, though. Okay, because you're dealing with scalar quantities like like energy and work, which are both scalar. Right? All right, that sort of makes sense. We're going to do a bunch of these, so if the first one didn't make sense, don't panic. Okay, we're going to be spending a fair amount of time on this. All right, I want you guys to copy this one down and try it. It's very much like the one we just did. Okay, so as we read through this question, it says, a tractor pushes a rock with a mass of 550 kilograms. So first thing I'm going to do is write down my mass that I was given there. Okay, from rest to a speed of 4 meters per second. Okay, so I was given mass, initial, and final velocities. Okay, they're asking me, and then they say that happens over a distance of 25 meters. What force is exerted? All right, so looking at my givens and looking at the context of my question here, force and distance are part of this. So is work being done? It is. The other way I know work is being done is because what's changing about the rock? Okay, it's moving. What else is changing about it? Okay, that's distance, position, same thing. Its speed is changing. If its speed is changing, what else is changing about it that has to do with work? It's energy. What kind? Kinetic. Remember, kinetic energy has to do with movement. This thing is moving and it's changing its speed. Okay? Potential energy has to do with height. All right? So we're changing the speed of this, and we know, guys, okay, this is the thing we got to remember. We know that the formula for kinetic energy is 1/2 times mass times speed squared. Remember I told you, write down your givens and look at your formula sheet. All right? You have force, distance, mass, and speed. Okay? You got to look for formulas that hold those things. All right? Now, since I know that there is a change in energy, I know that work is being done, I got to set this up as a work energy theorem question. Work is a change in energy. In this case, specifically, it is kinetic energy because the speed of the rock is changing. Okay? I'm not pushing the rock up a hill. Okay? It never mentions its height changing, so I know potential energy is not involved. All right, the formula for work is force times distance. That's good, because I'm supposed to find force. I'd better have a formula on here that has it in it. And change in kinetic energy means 1/2 mvf squared, that's my final kinetic energy, minus my initial kinetic energy, 1/2 mvi squared. Can I simplify my formula a little bit? What can I get rid of? Riley? Right. If VI is 0, then all of this is 0. Gone. All right. So now I'm left with force times distance equals 1/2 mvf squared. This is exactly like the last one. Right? So far it is anyway. Okay? Force times distance equals 1/2 mv squared. It's actually a little easier mathematically, because I'm not going to have to worry about the square roots or anything. Right, Elizabeth? Stop texting. Now, I've got to find force. How do I get force by itself? Okay, what do I divide over? Well, I want to leave that over there. I want to get force by itself. What do I have to move? Right, I got to move the distance. So I'm going to divide both sides by d. Now force is by itself. And I have all of the stuff that's on the other side. Okay? So force is going to equal 1/2 times 550, the mass of the rock, times the speed of the rock, the final speed of the rock in this case, 4, and that's squared, divided by d, which is 25 meters. Okay, so 0.5 times 550 times 16, that's 4 squared, I'm just shortcutting a little bit here, okay, divided by 25. All right, so I'm going to have to use 176 newtons of force. Okay, it's going to take a little bit of getting used to. Okay, physics is really, in Science 10, really the first time you ever really have to read a question in this way. Okay, you can get in chemistry next year. You'll have to do that for chemistry too. Okay, in chemistry and Science 10, you didn't really have to because it was really kind of cookbook. Right, you just well, I just follow the steps and everything's good. Okay, in these ones you got to do a little bit more interpretation. Questions on that one? All right, try this one. Okay, write it down first, and then give it a try. I'll give you a few minutes on it. Okay, so we got a mail carrier who picks up a 10 kilogram package on the 3rd floor of a building, 30 meters above the ground, and then delivers it to the 10th floor, 100 meters above the ground. What's changing in this question? Height. What kind of energy is height part of? Potential. All right, so here's what we got to do. Okay, work is a change in, this time, potential energy. Okay, we want to write down what we're given. First off, we're told the mass of the package, 10 kilograms. We're told the initial height, 30 meters. We're told the final height, 100 meters. Okay, how much work is done? All right, well, it says here in my formula that work is a change in energy. So I don't even have to do the force times distance stuff here, do I? Which is good because I wasn't given either one. Okay, it'd be pretty difficult to do it that way. All right, so work is a change in potential energy. So I'm going to take my final potential energy, m times g times h final, and subtract my initial potential energy, m times g times initial height. Okay, do I have all those numbers? I have m. Okay, g is on my formula sheet. It's always 9.81. And I have the two heights. So all I have to do is plug in my numbers and solve. Okay, so work will equal 10 times 9.81 times 100, my final height, minus 10 times 9.81 times 30. Okay, so this mail carrier is going to do 6,867 joules of work in carrying that 10 kilogram package up 7 floors. Okay? Because it's work. Work and energy have to have the same units. If work's a change in energy, they have to have the same units. You can do that, okay? And if you understand math, you're okay to do it that way. The problem is a lot of people over-apply that to the 1/2 mv squared, and you can't use it in that formula. A lot of people will go, oh, I'll just subtract the velocities and square it and then multiply it by 1/2 of m, and it doesn't work. Okay? It doesn't work in the kinetic energy formula. So I never show it that way, but you're right. You could do it that way in this formula, okay? But you can't do it for kinetic, okay? All right, questions on how that one worked? Is this starting to make a little more sense now? We seemed a little more confident with that one. Okay? All right. Try this one. We're back to speed again, so we're probably dealing with kinetic energy, right? Oh, sorry, guys. And I pressed the record button right before that happens, right? And you get paralyzed by the sneeze. Okay. So, we got a bulldozer, and it does 7,500 joules worth of work. Okay, so we're told the work, 7,500 joules. Okay, and it pushes a truck from a speed of 2 meters per second, okay, to an unknown speed. If the truck, okay, so that means VF is unknown, okay, and the truck has a mass of 2,500 kilograms. Okay, what is its final speed? What kind of energy is being changed? Kinetic. The speed of the truck is changing. It mentions nothing about it being pushed uphill or anything like that, so there's no potential energy change here. All right. Work is a change in kinetic energy. Okay, so that means that work equals 1/2 mvf squared minus 1/2 mvi squared. I'm looking for VF. So, what do I do in order to get VF by itself first? The rules of algebra say if I want to move something, I do the opposite. What I do to one side, I do to the other. And I move what's not attached first. Right now, what's not attached to VF? Yeah, this whole thing is not attached, right? This whole term is not attached to VF. Can I move it all at once? Yes, I can. Okay? Because if I was solving this, if I was actually solving for work, I would figure out what 1/2 mvf squared equals. I would figure out what 1/2 mvi equals, and then I would subtract them. So there's nothing wrong with me adding 1/2 mvi to both sides right off the bat. Okay? So that's what I'm going to do. I'm going to go work plus 1/2 mvi squared equals 1/2 mvf squared. All right, so I've moved one big part of it. I still need to get VF by itself, so what do I have to do with the 1/2 of m? Divide it, right. Now here's where people often make a mistake. They look on the top and they look on the bottom, they go, hey, there's 1/2 of m both on the top and the bottom. That means it cancels. Does it really cancel? It doesn't. Okay, here's why. This 1/2 of m is already involved in some other operations. It can't be canceled right now. Okay, so it's got to stay there top and bottom. Now, that's set up to find VF squared. I want to find just VF. So what do I have to do? Square root. Okay, now I can plug in my numbers. And that's a pretty complex manipulation, I'll give you that. Okay, it's tricky. Okay. So VF equals the square root of the work, 7,500 joules. It was nice of them to give us that number. Okay, plus 1/2 times the mass, which was 2,500. Okay, times the initial velocity or initial speed, 2 squared. Okay, divided by 1/2 times 2,500. Right, that's what my formula said I needed to do. All right, so again, rather than try and take chances on being able to do the brackets right, okay, I'm just going to make sure I get it right. So minus 0.5 times 2,500. I probably didn't need that bracket there, but I put it, oh sorry, it's not supposed to be minus, it's supposed to be plus. No, that was dumb. Don't need the brackets, so I'm going to set a good example here. Times 2,500 times, okay, 2 squared, which is 4. All right, so I'll do that, and then divide that by 1/2 of 2,500, which I'll do in my head is 1,250. Okay, so that gives me, yeah, of course it is. It should give me 10, because 12,500 divided by 1,250 should be 10. Okay, now what do I have to do with that number? I still haven't done. I haven't square rooted it yet. All right, so the final speed of this truck is 3.16 meters per second. Didn't speed up very much, did it? It went from 2 to 3.16 meters per second. Well, it's a big truck, right? So yeah, it's probably not going to speed up all that much being pushed by a bulldozer, which doesn't move all that fast. Okay, so 3.16 meters per second. Okay. Is there a pattern here to what we're doing? Right? They all start out with write your givens down, then figure out what kind of energy is being changed, then set up works to change in energy, and then manipulate for what you're looking for and solve. Okay? That's essentially the pattern we're going to go through. So we're going to write those down. This isn't in your notes. Okay? So these are kind of the steps or tips for solving work energy theorem questions. First thing you do is you write out your givens. And then you can look at your formulas here. Work's a change in energy, or force times distance is a change in energy. Once we've done that, okay, then we have to identify the type of energy that's being changed. Okay, and was that exactly the next thing I did on every one of those examples? Right? Wrote down the givens and then said, okay, what's changing? Oh, velocity is changing. That means kinetic energy is changing. Oh, height's changing. That means potential energy is changing. Okay, so we figure out what kind of energy is being changed, and then we know which formula we're going to have to use. Are we going to have to use m times g times h because it's potential, or are we going to have to use 1/2 mv squared because it's kinetic? Once we know that, we set up the work energy theorem. Change in energy equals final minus initial. All right? And for a potential energy problem, it looks like this. Force times distance equals mghf minus mghi. If it's kinetic energy problem, it looks like this. Okay? 1/2 mvf squared minus 1/2 mvi squared. All right? Then you manipulate and solve. Okay, so this one talks about a person using an unknown force to lift something. Okay, a 50 kilogram mass to a height of 1.5 meters. All right, so I want you guys to try that one. See if you can figure out how much force was used. Mathematically, this one's quite easy. Okay, as long as you can understand the one tiny little trick that's in it. Okay. So, using an unknown force, okay, to lift something. So what kind of energy is changing? Potential energy is changing. All right, so the work equals the change in potential energy. Now, it doesn't say so, but we have to assume that it was lifted from where? From zero, from the ground. Okay, so how much potential energy does something have when it's on the ground? Zero. All right, so can I say then that force times distance equals m times g times h? And just leave it at that. Right? Because this is mghf, really. I mean, if it didn't have any potential energy at the beginning, then it doesn't really matter that I don't write it. Right? All I got to do is manipulate for force. That means divide by distance. Here's the trick. Are the distance and the height the same number? Yeah. When I lift something 1.5 meters, I exert a force on it for 1.5 meters. So here's what ends up happening. Okay, when you plug in your numbers, D and HF cancel each other, and you're left with force equals m times g. Look on your formula sheet. Is there a force on your formula sheet that's equal to m times g? We talked about it yesterday. The force of gravity. Okay, that's what you work against when you lift something, so it's logical that it should equal the force of gravity. 9.81 times the mass. All right.